So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be proving this integral from 0 to infinity of x to the n minus 1 over 1 plus x dx equals pi over sine pi n. This integral. And you know what? I have uploaded a proof of this integral a couple of months ago actually. If you are a daily viewer and if you are a viewer from that time of my channel, so you might have an idea about that. So basically why I'm talking about that in this video, isn't that weird? But it's not actually. It was too long. I think I just crossed 40 or 50 minutes to solve this integral. And I did use a lot of things. And here's a soft copy of that, I would say, a hard copy of actually. And yeah, I have just solved it. The work I have done in that video, this is the work that I have done in that video actually. So basically, if you can watch all things clearly, so we have considered the Fourier series of f of x equals cosine of ax, and that too from negative pi to pi, and then we just solved this Fourier series actually, and then we just reached up to this series right over here, 1 over a plus the sum as k goes from 1 to infinity of 2a times negative 1 to the k over k squared, a squared minus k squared equals pi over sine of a pi, right? Okay, so far it's good. And now we have considered the actually the integral, and here's the integral actually, right? So we have considered that, and we just did some sort of manipulations over there, and then we did introduce an infinite series actually right over here, and then we just plugged that actually, you know what, we know that 1 over 1 minus x can be represented as the sum as k goes from 0 to infinity of x to the k, right? So from that from that point of view, we can talk about 1 over 1 plus x as well. So basically it's gonna be the sum as k goes from 0 to infinity of negative 1 to the k times x to the k. And yeah, we did use that thing, and then we just reached up to, after this sort of manipulations, we just reached up to I equals this exact sum that we had here. So basically from this equation and from this very equation, we just proved that the integral is equal to this sum. This result actually. So it was a difficult task actually, and you know what? Maybe you can say I wasn't sure about the easiest way of doing this, and that is the beta function. So yeah, I have uploaded an introductory video on beta function. If you want, you can check that out actually. So basically we are going to be proving this integral with the help of beta function, right? So I think it's let's just begin this out. And I'm extremely sorry guys, actually my AC is turned off because electricity has gone, so I'm just getting like sweat. Okay, I'm so sorry about that. So basically beta of let's say the beta function, so beta of m comma n is just the integral from 0 to 1. It's an integral representation of beta function, and it's 0 to 1 of x to the m minus 1 times 1 minus x to the n minus 1 dx. And we have proved this, that beta of m comma n is also equals to gamma of m times gamma of n over gamma of m plus n. So basically we have talked about this beta function in the introductory part of this beta function, right? So yeah, I have proved this, and you can check that out if you want. So basically we are just going to play around with this integral first, and then we'll talk about this later on. And guess what, we're going to be using the Euler's reflection formula as well, but that will be in the last of this video. So let's just talk about the integral. So we are having, let's say, beta of m comma n as integral from 0 to 1 of x to the m minus 1, 1 minus x to the n minus 1 dx, right? So here we are going to substitute x equals 1 over 1 plus y. So if we talk about this substitution, so let's just isolate y. So it's going to be xy plus x actually equals 1. So y is going to be your 1 minus x over x. And if we talk about the differential, so dx is going to be negative 1 over 1 plus y whole squared. Okay, so from this equation, when we plug x0 actually, so it's gonna be 1 over 0, which is gonna be helping us to that the lower bound is gonna be tending to infinity. So basically, when x is 0, y tends to infinity, and when x is 1 here, so y is gonna be 0, right? So when x is 1, y is gonna be 0. So basically, we are having beta of n, and its integral from infinity to 0 of your x is being replaced with 1 over 1 plus y. So it's 1 over 1 plus y whole to the m minus 1, and times 1 minus 1 over 1 plus y to the n minus 1, and we are having the differential, that is minus 1 over 1 plus y whole squared dy. And guess what? This negative sign is going to help us to just replace, actually interchange the bounds, because that's an improper integral over there. So let's just write that down. Okay, so yeah, so beta of m comma n is going to be integral from 0 to infinity, and that can be written as 1 over 1 plus y to the m minus 1, and this can be written as 1 y plus 1 minus 1 over 1 plus y whole to the n minus 1, right? Okay, and then we are having 1 over 1 plus y whole squared dy, and then beta of n, m comma n actually, it's the integral from 0 to infinity, and this can, since this plus and minus 1 are going to cancel out with each other, and we would be having 1 over 1 plus y to the n minus 1, and it's y to the n minus 1 over 1 plus y to the n minus 1, and over 1 plus y to the squared dy. And again, beta of m comma n is going to be integral from 0 to infinity, and multiplying these denominators, right? Basically, numerator is going to be y to the n minus 1 over, it's 1 plus y to the n minus 1 plus n minus 1 plus 2. So minus 1 and plus 2 are going to cancel out with each other, and finally we are having our beta of m comma n as integral from 0 to infinity of y to the n minus 1 over 1 plus y to the m plus n dy. Okay, and now we are gonna be using the gamma relation between the beta function and the gamma actually beta function, right? Okay, so basically our beta function is beta of m comma n is integral from 0 to infinity, and it's y to the m minus 1 over 1 plus y to the m plus n dy. And we know that it is equivalent to gamma of n times gamma of n over gamma of n plus n. And you know what? If we plug m plus n equals 1, so that's going to be giving us the same exact integral that we are here for. So from this equation we can say m equals 1 minus n. So integral is going to be y to the n minus 1 over 1 plus y, right? Because m plus n is 1, and here we are having gamma of 1 minus n times gamma of n over gamma of 1, and gamma of 1 is just 1, and gamma of n times gamma of 1 minus n. From the Euler's reflection formula, we can say this is equals to pi over sine pi n, and hence prove. Guys, literally it was too easy. It was damn too easy. It wasn't difficult at all, right? So yeah, that's how we can talk about this, and it's pretty easy actually. The work that I have done in that video is far, like, this one is far more safer than that, and easily understandable than that actually. So yeah, guys, I'm just having some sort of sore on my body, so I need to just cut off this video right now, because maybe you're gonna feel disgusting about my looks. Okay, goodbye guys, take care, love you, and again guys, if you got to learn something out of it, please make sure to like, subscribe, and share. And if you haven't got out so far, you are free to ask me in the comment section. I'll be there to reply over your questions. Thank you guys, goodbye, take care.